Hello everyone. We are going to go over 7.3 sample means. Third time's the charm. Hopefully this video will actually record for y'all. Alright, our essential question is how do we calculate the mean and standard deviation of a sample mean x bar? Alright, so 7.2 is all about p hat, which is our population proportion is p, and then our sample proportion is p hat. And so now, instead of looking at mean mu and sample mean x, instead we are now looking at mean mu and sample mean x bar. Alright, so remember that mu, so the mean of a sampling distribution of x bar is the sample mean, is always going to be equal to mu of x bar is just going to be equal to our mu. So the mean of the standard means, of the sample means is always just going to be mu. Okay. If the 10% condition is satisfied, lowercase n is less than or equal to 1 over 10 uppercase n, or you could say that 10 times the lowercase n is less than or equal to uppercase n. Then we can say that the standard deviation of x bar, the sample mean, is sigma sub x bar is equal to sigma divided by the square root of n. Remember that n is going to be the total members of a population, and lowercase n is the sample size. So as long as you're dealing with less than 10%, you're not looking at more than 10% of all the people in the population, then our 10% condition is satisfied, and everything about the behavior of x bar is similar to p hat behavior, except we don't have to prove it is approximate. Okay? That is approximately normal to find the standard deviation or mean. If you want to find the probability of something, though, you need to know the x bar was taken from approximately normal data, an approximately normal data distribution. So here's our example. A bottling company uses a filling machine to fill plastic bottles with cola. The bottles are supposed to contain 300 milliliters, but really the contents are normally distributed with a mean mu equal to 298 milliliters and standard deviation sigma equal to 3 milliliters. What is the probability that a randomly selected bottle, so a single bottle, contains less than 295? So when we are dealing with a single thing, it's just going to be the same as we've always done. You've got your normal CDF, we're going to put our lower in, we're going to just make up a big number, negative 10,000. Our upper, if we want to have it less than 295, our mu is still going to be 298. That's what we have here, and our standard deviation is 3. So we have 0.1587. The probability that a single selected bottle contains less than 295 milliliters is 0.1587. So sometimes we care about just one thing happening, but what if we want to look at like a group of things? This is when our sample comes in, and that's when we have to look at the sample mean, okay? So what is the probability that the mean contents, or the average contents, of 6 randomly selected bottles is less than 295 milliliters? Are you getting gypped if you get the 6-pack? That's what we want to know. So you have a 15% chance of getting a bottle that is less than 295 milliliters if you just grab a single bottle, but what happens if you get a 6-pack? Because this is, you usually just don't buy one bottle at a time unless you're just going to Stripes, okay? So we have mu sub x bar is equal to mu, so it's still going to be 298. Alright. Now, because 6 is less than 10% of all bottles produced, we've met our 10% condition. We're going to guess that the factory is making more than 60 bottles. Then sigma sub x bar is equal to sigma divided by the square root of n. So remember that sigma was 3, and our sample size is 6. And if you do 3 divided by the square root of 6, we get 1.2247 milliliters. So now we got our new normal CDF. Our lower end is negative 1,000, upper 295, mu 298. Sigma is the only thing that's changed, and it's smaller. And you would expect it to be smaller because with a larger sample, there's less variability, right? Okay, so we get 0.0072, so there's less than a 1% chance. So there is a 0.0072 probability that x bar, or the sample mean of 6 simple randomly selected bottles, is less than 295 milliliters. So you got a pretty good chance that it's all going to even out in the end. Now the central limit theorem, the CLT, says that the sampling distribution of x bar, the sample means, approaches a normal distribution as n, the sample size, gets larger, no matter the shape of the population. So it doesn't matter if it was skewed left, skewed right, as long as you have a sample size larger than 30, we can apply the central limit theorem, the CLT, to a non-normal distributions and say the sampling distribution of x bar is approximately normal. So when you pull a sample greater than size 30, even from non-normal distributions, so skewed left, skewed right, it still ends up being normal because we have a large sample size. Okay, so it's the central limit theorem. So let's apply it. So we got David's iPod has about 10,000 songs. The distribution of the song lengths is heavily skewed to the right, meaning there are some long songs out as outliers. So you got those songs that are over 18, 19 minutes long, but there's gonna be a concentration of songs that are those short intro songs. Then you got the 1-minute songs, 2-minute songs, 3-minute songs, 4-minute songs, and the longer songs, they are rarer. But you've still got those really long ones that are just making it heavily skewed to the right. So if we look at this, there is a mean of 225 seconds per song and a standard deviation of 60 seconds. All right. So we cannot. Why can we not calculate the probabilities of a mean of a simple random sample of 10 songs? Well, because 10 is less than 30, the central limit theorem is not met, and it's too heavily skewed to the right. So you're more likely to get a random assortment of a long song that gives us biased data, and so we can't calculate probabilities of sample size 10. But let's calculate the probability that the sample mean of 36 songs is greater than 240 seconds. So first, because n is equal to 36, which is greater than 30, we will apply the central limit theorem and say that the sampling distribution of x bar is approximately normal. You need to establish why you can go ahead and call it normal. Okay, so you have to invoke the central limit theorem. So we get mu sub x bar is equal to mu is equal to 225, because we had 225 seconds as our mean. All right. Also, because 10 times 36, so we still have to make sure the 10% condition is met, is less than 10,000. There, 10% condition is met, and now we can say that sigma sub x bar is equal to sigma divided by the square root of n. So we get there was a standard deviation of 60, and our sample size is 36. Well, the square root of 36 is 6, so 60 divided by 6 is 10. Alright, so now we want to find the probability that x bar is greater than 240. So we use the normal CDF. The lower end is 240, upper end 10,000. Just pick a big number, but we picked our lower end from here. Mu is 225 because it's the sample, that's the mean, so that's our mean of our sample means. And our sigma, our standard deviation, is 10 from here. And if we calculate that, we have a 0.0668. So we can say that when randomly selecting songs of sample size 36, the probability that the sample mean is greater than 240 seconds is 0.0668. Alright, make sure you're reading the 7.2, 7.3. We're going to have a test grade over the notes and a reading quiz combined on Tuesday, January 7th when you get back. So hope y'all are having a fantastic break. Have a Happy New Year's at this point, and we'll see you soon.